Yes, now to the ionization energy, and we defined it in the last part that it is the minimum amount of energy required for to remove an electron from the outermost energy level of an atom in its gaseous state. That is what we said the first ionization energy is. When it comes to alkaline earth metals, we have just said it now that it is to remove an electron. To remove an electron. Remove this electron. Remove an electron from the outermost energy level of an atom. Therefore, that one was applying in alkaline metals because they only have one electron in the outermost energy level. For alkaline earth metals, they have multiple. They have two electrons. Two. The same case to magnesium. Two electrons are there. So we'll be having the first ionization energy and the second ionization energy. First ionization energy, to remove the first electron. Second ionization energy, it will be now the energy that will be required to remove the second electron. And when we talk of the first ionization energy and the second ionization energy, there now arises a question. Which energy now will be bigger than which? Is it the first which will be bigger than the second, or is it the second which will be bigger than the first? We will answer that. But before we do that, let us now first talk of the trend of the first ionization energy, or the ionization energy, the trend in this group, alkaline earth metals. How does the ionization energy trend? Does it increase or decrease down the group? We said we describe down the group, but if you prefer up the group, it's all fine. So we are now talking of ionization energy of alkaline earth metals. The energy required to remove the first electron, or to remove an electron, when you say and we refer to one, from the outermost energy level of an atom in its gaseous state. We compare that of calcium and beryllium. The energy required, okay, the same point we said at first is still to be followed, that beryllium has a small atom, and therefore, and the same case was applying to lithium, a small atom, and therefore the electrons of beryllium are experience a higher nuclear attraction. Yes, that is the term. Experience. Okay, that is it. As a result of it having a smaller atom, the electrons of beryllium experience a higher nuclear attraction. That is attraction to the nucleus, nuclear attraction. So it will be the same case to lithium. So the smaller the atom, the higher the nuclear attraction. We have positive charges here pulling electrons, positive charges pulling electrons here. Yes, so the smaller the atom, the higher the nuclear attraction. But for these ones, which are very far from the nucleus, there will be lower nuclear attraction. Of course, there will be attraction still, because it is one holding the atom together. There will be attraction, but it will not be strong. So these ones experience a higher one. We are talking of the ionization energy. Yeah, the ionization energy. And now we have talked of losing of electrons, and the ionization energy, i.e., is the minimum amount of energy required to remove it. So which one, just as we did in alkali metals, which one will require more energy? Ionization energy. Which one requires more energy for it to be removed? You see that one, this one has a stronger nuclear attraction. It will take a lot of energy to pull it from its atom. It will take a lot of energy to remove it. And since it will take a lot of energy, it means the ionization energy is high. Yes, because it is the energy required to remove, so it is high because it takes a lot of energy. This one it has a big atom, hence it has less nuclear attraction, and therefore it only requires a small energy for an electron to be removed. Magnesium is here at the center. This one requires a lot of energy, but for magnesium it will not require as much. Itakuwa kubwa kuliko hii. Yes, it will be greater than this, but smaller than, sorry, it will be smaller than this, but greater than this. Let us show the trend. We are talking of the first ionization energy. The first ionization energy you can't remove. These ones require a lot of energy because the small atom requires a lot of energy as compared to these two. This one is the highest. So the energy, let us remove that arrow. The energy is biggest in beryllium. Magnesium is also big, but not as big as beryllium. And calcium will be the smallest. And therefore we draw our arrow upwards. That is the arrow. And what does it mean? It means that the ionic ionization energy, oh my god, the name had got off me. I mean, the ionization energy increases up the group. Yes. Oh, no. We said we describe down. But if you have to say up, it increases up the group. Let us use this arrow. We want to say down. Yes, we want to say down the group. Down the group. This one is the biggest. This one is the biggest. This one requires a small amount of energy, and therefore it is decreasing. It is decreasing. So ionization energy, the first ionization energy decreases down the group. Concluded. The first ionization energy, or generally the ionization energy, because the second one will follow the same suit, the ionization energy decreases down the group. This one requires more energy, and therefore it has the highest ionization energy. Maybe let us mention the figures. Ionization energy for alkaline earth metals. I want to get to the table. A minute, please. And here I am. Ionization energy for, we write that one of beryllium, that one of magnesium and calcium. Ionization energy for beryllium is, the first one is 900. First ionization energy 900 for beryllium. We have magnesium is 736, and then we have calcium is 590. We can see very clearly that it is decreasing down the group, down meaning from the topmost element downwards. And then you can just mention that of barium. It is the, we have strontium there. Let me mention that of barium. It is the outermost in this table. Barium has 503. So the ionization energy decreases down the group as displayed by these numbers: 900 to 700, 590, 543. It decreases down the group. Then we have second ionization energy. And now, because I've drawn this table, let me extend it here and say this is first. And here we write about the second ionization energy. So the first is removing one electron from the outermost energy level. Second ionization energy, it will be removing the other electron. The other electron, because you are removing the first one and the second one, and by that it will gain stability. By that it will gain stability. So I've written the first ionization energy and we have discussed its trend. Now we're going to discuss the second ionization energy. Yes, the second ionization energy. And coming to this, first, before you write the values, we still ask ourselves, beryllium, the first ionization energy, beryllium was 2,2. Now beryllium has lost one electron to the first ionization energy. Some energy has been introduced, it has lost one electron. Therefore, we have beryllium here now. That is the nucleus of beryllium. And then it has two energy levels, 1 and 2, which previously it was 2, 2. Previously it was 2, 2. In here, beryllium has protons and neutrons. And it being atomic number 4, it has 4 protons. When you say 4 protons, you'll be thinking of 4 positive charges. It has 4 positive charges, attracting 4 negative charges, 4 electrons. 4 positive charges attracting 4 negative charges. But they have been introduced some energy, the first ionization energy, which took away this electron. One electron was taken away by the first ionization energy. So we are left with, remember we have just said that the positive charges in the nucleus are the ones attracting the negative charges. Now we'll be having 4 positive charges in the nucleus, 4 positive charges attracting 3 negative charges. 4 positive charges attracting 3 negative charges. Previously, it was 4 positive charges attracting 4 negative charges. They were balancing. So it was neutral. They were balancing. But now, one electron is lost. It was 4 electrons. That is 2, 1. So we have 4 positive charges attracting 3. And now in this process now, it will be like we have an imbalance of charges. Not just an imbalance, but now the nucleus is now even stronger. It was attracting 4 electrons, but now it is attracting just 3. It was attracting 4. Now it is attracting 3. And what does it mean? The attraction is even stronger now. It was strong at first, but now it is even stronger. It is even stronger. I said so much. I talked so much. But what I wanted now us to understand is which energy is more. Is it the first energy level? Sorry, is it the first ionization energy or the second ionization energy? Which energy will be more? Because the first one is removing this one, which has been removed. The second one now is coming for another electron here. But remember, this time they are being pulled even more. They are being pulled even more. And since they are being pulled more, it means even more energy will be required for it to be removed. Now you're coming for another electron and I'm pulling my electrons even more. Therefore, you will require more energy. So we expect the figure that we write here to be more than 900. That is all I wanted to say. The figure here will be more than 900. And this will be it is a common question in papers. They ask, which is greater? Is it the second ionization energy or the first ionization energy? That is what they ask. So you have to say, you have to reason out and say, some maybe know, they may know by cramming, but for me, or maybe for some of you, we may prefer reasoning out like this. And it must not take you 5 minutes. I know it took a bit long to explain it, but reasoning out this one must not take you too long. I'm trying to reason out and also make you understand. So that's why maybe I ended up spending a little more time. But now the thing is, you expect the figure here to be more. But all the same, the trend will be the same. It decreases down the group. The ionization energy decreases down the group. Yeah, decrease down the group. Let me now paste the values for the second ionization energy. It means it will be more than 900 to take the second, this other electron, for it to be taken, so that it can form an ion. For it to be taken away like that, there will be more energy needed. Let's paste the values here, and here they are. The second ionization energy for beryllium is none other than double this one, which is 1800. 1450, 1150, 1450, 1150. And then for barium or barium is 970. Generally, for each of these elements, the second ionization energy is greater than the first ionization energy. And second thing to note is that it is also decreasing down the group. Decreasing down the group. So there was some more content here on ionization energy as compared to alkali metals, but we are done and you have seen the trend and compared the first ionization energy to the second ionization energy. Next, melting and boiling points. Melting and boiling points. It revolves around the same thing. How strong is the atom? And I remember in the previous when you are learning about alkali metals, we just mentioned about the metallic bond, and we said that a metallic bond is affected by two things: the size of the atom. Good. Secondly, the number of delocalized electrons. But then we said if whatever you're comparing has the same number of delocalized electrons, like in this case, beryllium has two, magnesium has two, calcium has two, they all have the same number of delocalized electrons. You can't compare them using that fact of delocalized electrons. No. Therefore, we'll be comparing them by referring to the sizes of the atom. Yes, factor number one that affects the strength of a metallic bond, the size of an atom. We said if you have a small atom, we said that the smaller the atom, the stronger the nuclear charge. Let me draw the atom of beryllium again. Yeah, beryllium. Or let us use this. Beryllium attracts electrons more as compared to calcium because it's alpha. The nuclear charge in beryllium is high, a high nuclear attraction as compared to calcium. Therefore, for beryllium, yes, for beryllium, since the nuclear charge is high, nuclear charge, since the nuclear charge is high, it forms a strong metallic bond. And for metallic structure, I can draw one here. A metallic structure usually have atoms packed together. Just atoms of the elements. These are nucleus. Let us say this that of beryllium. And since the atoms are too small, they are packed like that. That can be seen in the topic structure and bonding. These are atoms of beryllium. Since they are very close together, they even attract. This atom will attract this one more because the size is small. This one will attract this one more because the size is small. Yes, good. But if we have big atoms like those of calcium, the attraction becomes poor. The metallic bond, we said, generally is a strong bond. But if you have big sizes of atoms, the bond is not as strong as for small atoms. We are looking at the melting point and boiling point of these alkaline earth metals. We have said that this one is stronger than this one. So we can ask ourselves, which one requires more energy for it to break? When heated, so the energy now will be from heating. When you're heating them, which one will require more energy? Is it beryllium or is it calcium? And definitely the answer will be beryllium because it forms strong metallic bonds. It forms strong metallic bonds. And since it forms strong metallic bonds, it has a high melting point. It has a high melting point as compared to calcium. The same case to magnesium. Let us show it using this arrow. The melting points and the boiling points. We have just said that beryllium is higher because it has a small atom leading to a very strong metallic bond and hence a strong metallic structure. We are talking of boiling and melting points. This is our arrow, or we said we still discuss it and state downwards. So downwards, the boiling and melting point, this one is big. This is the biggest, but it goes on decreasing. I just said it. It decreases down the group. Good. It decreases down the group. We have talked of melting and boiling points. Let us now talk of electric conductivity and then the last part, reactivity. So, electrical conductivity, beryllium and calcium. We said earlier that metals conduct electricity because of the presence of delocalized electrons. Metals conduct electricity due to the presence of delocalized electrons. And then we just said each of these elements has two delocalized electrons. And then they are metals. All metals conduct electricity. That is true. All metals conduct electricity. So they are all good conductors of electricity. And since they have, each of them has two delocalized electrons, then we can't compare. We say that this one is conducting more than this. No. We just say they are good conductors of electricity. Yes, they are good conductors of electricity. But you can compare them to this. Group 1 metals, alkaline metals. These ones have two delocalized electrons. These ones have one delocalized electrons. Which ones are good conductors? The more the number of delocalized electrons, the better the conductor that metal is. So magnesium, calcium, and beryllium conduct electricity better than lithium, sodium, and potassium. Electric conductivity. Let us talk of the last factor, which is the reactivity. Now, reactivity, and when you say reactivity, they are just referring to how they react. Reactivity. Reactivity. Which one is more reactive than the other? Which one reacts more? Beryllium, magnesium, calcium. On the atoms you have beryllium and calcium. Which one reacts more? A reaction will take place when a metal loses, or when an element, an atom, loses or gains. So, the easily you lose or gain, the easily. Do you lose easily or do you gain easily? The easily you lose or the easily you gain. Hiyo urahisi. It reflects itself in the reactivity. If you lose easily, then you react easily or you react fast. Therefore, you lose easily, you react fast. What am I saying? I just said the one that loses easily reacts better. Okay, beryllium and calcium. This atom is very big. This one is a small atom. This is, as you saw here, a small atom, a big atom. The nuclear charge here is strong. Protons pulling the electrons here. This one is strong. Therefore, it holds its electrons firmly. And if it holds them firmly, it means it does not lose easily. But this one, since it is very big, the atom is big, the nuclear charge is low. Low nuclear charge translates to it can lose electrons easily. It can lose electrons easily. It can lose electrons. Therefore, calcium is more reactive than beryllium. Yeah, calcium is more reactive than beryllium. Yes, because they react by losing electrons. This one can lose easily as compared to this. And that is what he said here. This one is very big as compared to lithium. And then it won't lose this electron to react. Now this one is firmly held. You don't lose it easily. This one is not firmly held. It can be lost easily. Potassium is more reactive than this lithium. And in this case, calcium is more reactive than the rest. And therefore for reactivity, we can use the using still our arrow here. What can we say about it? We are talking of reactivity. How reactive are they? Reactivity. This one is more reactive, but the arrow points downwards. You want to say it does this and this down the group. It does this and this down the group. We are referring to reactivity. This one is the most reactive. It increases down the group. It increases down the group. The reactivity increases down the group. So we are done with that. That means you are done with alkaline earth.